Welcome to the Explainer. Let's jump right in because today we're looking at a massive, massive breakthrough that might just completely reshape the timeline of human computing. We are breaking down some powerhouse new research coming out of the Department of Energy, Fermilab, and MIT Lincoln Laboratory. Now, if you follow quantum computing, you already know the potential is staggering. But, the roadblocks? They've been equally massive. Well, today, it looks like researchers might have just found a way to bypass the absolute biggest one of all. And that brings us to the ultimate question, right? How do we actually build a quantum computer with millions of qubits? For advanced applications, we're talking the kind of quantum computing that can solve the world's most pressing problems in medicine, cryptography, materials science. We literally need millions of these qubits working together. But simply adding more qubits isn't like, just snapping together Lego bricks. The physical space required, the extreme environments, and the sheer amount of control infrastructure needed are completely bottlenecking the physics right now. Section 1, the Quantum Scaling Challenge. Let's look at this roadblock. So today's quantum systems rely on this massive, totally impractical web of wiring. You know that messy tangle of cords behind your television set? Okay, multiply that by thousands. And then imagine those cables actually have to bridge electronics sitting at room temperature with delicate components sitting inside cryogenic freezers that are quite literally colder than deep space. You've got lasers, you've got extensive cabling spanning these massive temperature differences, and the problem is, as you add more qubits, you need more wires. Very, very quickly, the physical footprint of just the control wiring becomes completely impossible to scale up. Section 2, the power of ion traps. Well, what exactly is sitting inside those freezers that demands all this wiring in the first place? At the center of this specific breakthrough are ion traps. An ion trap basically uses electric or magnetic fields to capture and confine charged atoms, or ions, so they can be used as qubits. In this setup, they are the true beating heart of the quantum computer. Now, scientists absolutely prize these systems. They are fighting so hard to scale them up despite all those wiring nightmares for two really big reasons. First, long coherence times, meaning the qubits can actually hold their quantum state longer before the data degrades. And second, high-fidelity operations, which basically means the calculations are incredibly accurate. So it's the perfect foundation if, we could just stop drowning in a sea of cables. Section 3, the cryoelectronic breakthrough. This brings us to the core piece of technology making a solution possible, cryoelectronics. Developed heavily over at Fermilab, these are highly specialized circuits meticulously designed to operate in the extreme, sub-zero temperatures required for quantum computing. Look, this isn't your standard consumer silicon we're talking about here. This is hardware built to survive and actually calculate in the deepest freeze imaginable. The contrast here is honestly night and day. Remember the old setup? Room temperature controls passing signals through massive, bulky wiring all the way down into the freezer. But the new setup? The team from Fermilab and MIT Lincoln Laboratory completely bypassed the wiring nightmare. They took ultra-low power cryoelectronics and placed them inside the vacuum, right next to the ion traps. The control chip is now sitting directly in the cryogenic environment itself. It's a total game changer. Travis Humble, the director of the Quantum Science Center, captured the energy around this success perfectly. He called it an integration of state-of-the-art capabilities for scalable ion trap quantum computing. It's really a testament to what happens when Fermilab's deep microelectronics expertise collides with MIT Lincoln Laboratory's advanced ion trap platforms. But here's the best part. They didn't just propose this idea on paper. They actually built a proof-of-principle experiment to see if it worked. And spoiler alert, it did. Using these in-vacuum cryoelectronics, the team successfully proved they could perform the key functions necessary for a quantum computer. Step 1, they successfully moved individual ions. Step 2, they held them at set positions. And step 3, they were able to measure the effects of electronic noise, all while maintaining reduced thermal noise and improved sensitivity. The chip successfully acted as the conductor for the entire quantum orchestra, completely from inside the deep freeze. The really crucial takeaway here is just how much this accelerates our technological roadmap. Farah Fahim, head of Fermilab's macroelectronics division, emphasized that by showing low-power cryoelectronics can work inside these systems, we may be able to accelerate the timeline for scaling quantum computers, bringing closer into reach what seemed decades away. Think about that for a second. This isn't just an incremental step. This is a massive leap forward that dramatically shrinks the timeline of achieving quantum supremacy. And here is the staggering number this breakthrough actually unlocks: 10,000 plus. By eliminating the heavy, bulky wiring, these compact cryoelectronic chips could eventually support systems with tens of thousands of electrodes. And if you can efficiently control tens of thousands of electrodes, well, you pave a direct, highly realistic pathway to controlling the millions of qubits we need to basically change the world. Section 4, Lessons Learned and Next Steps. Now, true science is a process of iterating on extreme challenges, right? So obviously this wasn't completely flawless right out of the gate. The proof of principle test surfaced some tangible hurdles that are going to guide future chip designs. For instance, transistors that behaved perfectly back at Fermilab saw performance drops in MIT's significantly colder environment. Plus, while the circuits held voltages for milliseconds, they really need to push those hold times up to minutes or even hours for practical, large-scale systems. So what's the immediate next step for these researchers? The next big goal is integration. They plan to directly connect the control electronics with the ion trap chips. By creating an even tighter, more direct connection, they can further increase efficiency and performance, enabling the scaling of ion trap arrays for much, much larger and more powerful systems. Which leaves us with this final, really provocative thought inspired by MIT Lincoln Laboratories' Robert McConnell. He noted that this demonstration lays the firm foundation for hybrid integrated systems they hope to develop in the near future. So, are these ultra-cold hybrid integrated chips the final key to unlocking our quantum future? By solving the seemingly mundane, everyday problem of tangled wiring, these researchers might have just opened the door to the absolute next era of human computing. It is an incredibly fascinating space to watch, and we'll definitely be keeping a close eye on where this collaboration goes next.